class, so chapter 4 covers exponents, polynomials, and polynomial functions. The first section we're going to go over is the integer rules for exponents and how to use scientific notation. So a friendly reminder that an exponent is a whole number, right, that indicates how many times I'm raising a base number to be used as a factor. So if I say 8 to the third, that means I want to multiply 8 by itself 3 times. If I was to have 2 to the fourth, that means I want to take 2 times itself 4 times. It's mathematical shorthand is one way you could think of it. This is a lot faster to write than this. Here's our formal definition, if you're interested in that. But right now, I'm pretty sure we all have a grasp of what an exponent is. So here's a couple examples of exponents. I could say 9 squared, 2 cubed, 5 to the first power, and yes, we can raise things to the first power. We'll talk about that in this chapter. But after squared and cubed, there's no special name for like 3 to the fourth or 5 to the sixth. They don't have a special name. You can also take 9 to the 0 power, and we'll talk about raising integers to 0 powers in just a little bit. So any number other than 0 raised to the 0 power is 1. So 9 to the 0 power is 1. 5 to the 0 power is 1. Okay? Any number raised to the first power is itself, because basically that's saying, okay, I want to take 9 times itself 1 time. That just gives you 9. 5 to the first would be 5 as well. What's not defined is 0 to the 0 power, right? Because I said for any number not equal to 0, if I raise that to the 0 power, I get 1. But we wouldn't want to take 0 to the 0 power and get something, right? So this is undefined. So for example, if I have 6 to the 0 power, that is 1. If I have 5 to the 0 power plus 12 to the 0 power, that's 1 plus 1, okay? If I have 8 to the 0 power and k to the 0 power, that's going to give me 1 times 1, which is 1. It's important to note that because because variables represent a number, I can raise them to the 0 power and still get 1 as long as x doesn't equal 0. The first of our integer exponent rules is the product rule. So if a is really real number and r and s are integers, what I can do is I can take my exponents and add them. So for example, if I had 2 to the second times 2 to the third, that means I've got 2 2's and 3 2's. So how many 2's do I have? I have 1, 2, 3, 4, 5, which is the same as 2 plus 3. So that's why this rule works. So if I have 5 cubed times 5 to the first, that's 5 to the 3 plus 1, so 5 to the fourth. If I have x to the 8th times x to the 7th, that's x to the 8 plus 7, so I would get x to the 15th. If I have 3 to the 4th times 3 cubed times 3, I'm going to take 3 to the 4 plus 3 plus, remember this has an imaginary 1 up there because any number raised to the first power is itself. So I would have 3 to the 8th. Next, we're multiplying these two. So when we're multiplying, we need to multiply our coefficients. So that gives me a negative 15. But then I have y squared times y to the fourth, so y to the 2 plus 4. I have negative 15 y to the 6th. Our next rule is the negative exponent rule. Okay, it says that if r is an integer and I have a to the negative r, it equals 1 over r, a to the r. So if I had 3 to the negative 2, that's really 1/9, right? If I have 10 to the negative 1, that's 1/10 right? That kind of makes sense, right? If they represent a fraction, 1/10, also a decimal. So if I see a negative exponent in the denominator, if I see a negative exponent, I need to push that to the denominator and write it as a fraction. So here I have 2 to the negative third. That'd be 1/2 cubed. Here I have 5z to the negative 3, and that negative 3 is attached to the 5 and the z. So it can be 1/5z cubed, and I could expand that, right? I could have 5 cubed z cubed. It's entirely up to you. They are equivalent. For example 3, this z to the negative third power, right? That negative 3 is only on our z. So that gives me 5 times 1/z cubed. So I'd have 5/z cubed. Only the part with the negative exponent attached to it moves to the denominator. Which brings us to example 4. I have 1/2 to the negative third. Well, I would write that like we did in example 1, right? So now I have 1 divided by 1 to the cubed. This is called a complex fraction. It's when you have a fraction in your numerator and your denominator. Well, let's rewrite this. So this is 1 divided by 1/2. So I keep my first fraction the same. I change from division to multiplication, and I flip my second fraction. So I get 2/3. What does this tell us? If we have a negative exponent in my denominator, which is not where they belong, we move them to the numerator. So let's look at our last example, example 5. If I have 2 to the negative third over 3 to the negative 2, well, I know 2 to the negative third's got to go to the denominator. And we just saw in example 4 that 3 to the negative 2 has to go to the numerator. So that gives me 3 squared over 2 cubed.